Okay, so thanks Howard for the introduction. I guess and my surprise talk. So as the title of the surprise talk suggests, so I will talk about
Surprise context.
surprise context structures on spheres and applications thereof. So everything that I'll say today is based on joint work with Jonathan Bowden, Fabio, Gironella, and Zhengyi. So let me start with a bit of background. So this will be, talk of contact topology. So what is, well, contact topology? One could sort of informally say that it was, roughly speaking, the study of contact manifolds up to isotopy, where we allow ourselves enough freedom in order to wiggle things around. Contact manifolds being, odd-dimensional manifolds coming with some hyperplane distribution, which is maximally non-linear. And in this context, a way in which a contact manifold can arise is this, the contact boundary of a symplectic manifold, in which case we said that it is filled. So the fillability question in contact topology consists precisely into determining precisely which contact manifolds are fillable in this sense. And if so, we can sort of classify all the arising fillings up to some certain notion of isomorphism. There's also sort of a foundational important dichotomy introduced by Algebraic in dimension 3 and then generalized to high dimensions by Bormann, Algebraic, and Murphy. So roughly speaking, this says that, well, contact manifolds can come in precisely two types or two flavors. So either they are tight, in which case we think of them as being sort of a rigid or geometric object in nature, or over twisted, in which case we think they are sort of topological or flexible, because they satisfy a H principle in the sense of Gromov. So their classification is a matter of topology rather than geometry. Okay. And an early sort of application of the theory of pseudo-holomorphic curves is a theorem as Algebraic and Gromov relating these two sort of fundamental notions. Well, it says that fillable contact manifolds are tight. So in other words, over twisted contact manifolds cannot be fillable. And this is sort of, ideas going to Algebraic, sort of using moduli spaces of planes and so on. Okay, so this is a sort of bits and pieces of the field. In terms of existence, the first things that one needs to observe is that there are some obstructions in order for a contact structure to exist. The obvious underlying topological obstruction is this existence of an almost contact structure, which is, by definition, the tangent bundle of the manifold should admit a reduction of the structure group to the unitary group times the identity. So this is just saying that your manifold should come with some hyperplane and with some sort of almost complex structure on the hyperplane. So this shows, the existence of this is just purely topological. And there's a theorem that goes back at least to work of Lutz and Martinet in dimension 3, and then this work of Casals, Pancioli, and Princeton in dimension 5, and in arbitrary dimensions, this is Bormann, Algebraic, and Murphy again. So it says that, well, whenever the obvious topological obstruction vanishes, namely whenever you actually have an almost contact structure, then you actually do have a contact structure itself in the same sort of, let's say, formal class. And the contact structure that you find is actually over-twisted. So it's one of these sort of flexible ones. So over-twisted contact manifolds exist in abundance. And, the H principle says that, well, more or less classifying them is a matter of topology. So this leaves the question of, well, how can we actually try to understand the other ones, the tight manifolds? So it turns out that the world of tight manifolds is much more mysterious and complicated. So tight contact manifolds are hard to construct and let alone classify. Okay, so one approach to sort of this, try to understand the set of all tight manifolds is to introduce this hierarchy of fillability. So, contact manifolds sometimes are fillable, and the different types of fillings that you can find. So I will not get into sort of the definitions of each of them, but I'll roughly speaking describe. So there's a whole set of inclusions. So for example, you can look at the Stein manifolds with boundary contact manifolds. So this is basically a very sort of algebraic notion coming from, let's say, complex algebraic geometry. So Stein manifolds are properly embedded complex manifolds of Cn, so they're affine. So their holomorphic theory is very rich. On the symplectic side, there's this notion of a Weinstein manifold, which one obtains by attaching a sequence of Weinstein handles to the ball. And that sort of imposes certain topological constraints. So like the Betti numbers of the manifold go up only up to half of the dimension. And there's a pretty deep result of Eliashberg saying that the set of Stein-fillable contact manifolds coincides with the set of Weinstein fillable contact manifolds. So the Stein manifold is naturally Weinstein. This is saying that if you give me a Weinstein manifold with boundary contact manifold, then I can deform it to a Stein structure relative boundary. Okay, so that gives us inclusion on the first equality in the first inclusion, and then you can consider the set of Liouville fillable ones. So Liouville filling being an exact symplectic manifold, so we have an associated Liouville vector field which points outwards at the boundary. We can also consider the case of strong fillings, which one asks the symplectic manifold is exact only near the boundary. And then there's also a notion of weak fillability. In dimension 3, this is just saying that the symplectic form should be positive on the contact structure at the boundary. In high dimensions, this is a definition of Maslow and de Kruger and Wendell. So it's slightly more technical, basically says that there should be some J which is tamed both by the symplectic form and the derivative of the contact form at the boundary. Okay, so and these are sort of all inclusions, and they're all included into the set of type manifolds. And the fact that all the other inclusions, so 2 up to 5, are strict, is follows from work of several people. So I'm listing all the names here to give you an impression of how many people actually thought about it. So there's a difference between dimension 3 and high dimensions. So dimension 3 was studied early on. The case of high dimensions was only sort of more recently established. So for example, Bowden gives an example of a Liouville Venant Weinstein fillable contact manifold in dimension 3. Okay, so this is basically entails some sort of existence results. But we have examples, but the topology tends to be fairly complicated in general. Okay, so this is one way to approach sort of like a classification of tight manifolds. But another thing that you could try to do, right? The first steps that you could, in the classification type of approach of all tight contact manifolds, would be to try to simplify the standard topology as much as possible. So in other words, you consider the case of a sphere in all dimensions. And then you try to classify contact structures there. Of course, the sphere comes with a standard contact structure given by the boundary for standard symplectic ball. And the question is whether you can actually find others. So an early result of Eliashberg in 1991 proves that the 3-sphere, in the 3-sphere, there's a unique tight contact structure, which is just a standard one. So in particular, it's Stein-fillable. This follows from the theory of convex surfaces due to Zhou. Also, Eliashberg, around the same time, shows that for high-dimensional spheres, so spheres of dimension 5 and so on, these guys have non-standard fillable contact structures. And the way that he shows this is using another result attributed to Eliashberg, Fleur, McDuff, saying that if you take the standard contact structure on the sphere, then any fillings of it will be diffeomorphic to the ball. And Yasha gives fillings of contact structure which are not diffeomorphic to the ball, so in particular non-standard. But there's also results of Ustilovsky, 99, so he constructs infinitely many exotic structures on a sphere of dimension 4n plus 1. And then Geiges in 2004 lifts this sort of dimensional constraint. So they prove that every odd dimensional sphere has non-standard contact structures. There's also other results of Webele for certain spheres. And then more recently, there's some nice results of Alves and Maiwes in 2019. So they give exotic contact structures with sort of non-standard dynamical properties. So every rib flow for those contact structures has positive topological entry, which is rather sort of interesting. And then there's also a result of Lasaev giving flexible fillings for non-standard contact structures at spheres. And as far as I know, this is more or less everything that was known for non-standard structures on spheres in dimension 3 and higher. So the first theorem that I want to present to you today is sort of, let's say, an addition to the cabinet of oddities. So some surprising contact structures on the sphere. So the first thing to mention is that all of the above contact structures that I mentioned before are fillable. So the boundary of some symplectic manifold. So the theorem that we proved with Jonathan, Fabio, and Zhengyi very recently is that, well, in dimension at least 5, then the sphere admits a tight but actually non-fillable and homotopically standard contact structure. So this homotopically standard just says that the underlying almost contact structure is the same one as the standard, as the one induced by the standard contact structure. So in other words, like the classical topology, including the almost contact structure, are standard as standard as they can be. What's non-standard is the contact topology. And the nice thing about sort of having one of these exotic structures on a sphere is that we can implement it on any other manifold by connected sum. So by taking a connected sum with one of these non-standard spheres, we obtain the following corollary. So if you give me any strongly fillable contact manifold in dimension at least 5, and you need to assume some technicality, you need to assume that C1 is torsion, which we expect should not be necessary, but it's there anyways. Then the claim is that M admits a tight but not strongly fillable contact structure in the same underlying almost contact class. So you don't change the formal data, but you make it non-fillable. So this says that tight and non-fillable structures really exist in abundance in higher dimensions. So if you're having hopes of trying to classify anything in higher dimensions, this says, well, that this might be rather complicated. Any questions on the statement? Okay. So let me mention maybe the first examples of a tight but non-fillable structure was by 8, 9, and Honda in dimension 3, and in high dimensions, this is probably Massot, Niederkruger, and Wendell. Okay, so if M is actually Weinstein fillable and dimension is high enough, so in dimension at least 11, we can actually show that we get infinite many of them. Not just one, really many. This includes in particular the spheres. So the spheres of dimension at least 11 have infinitely many tight and non-fillable contact structures. Okay, so this addresses one of the inclusions in the hierarchy of fillings, but we can actually also construct other exotic structures which are Liouville but not Weinstein fillable in dimension at least 7. So the theorem by the same people is that for spheres of dimension at least 7, we have Liouville and non-Weinstein fillable structures. They're also again homotopically standard. So this is another one of the inclusions. So and again, by taking a connected sum, we deduce that if you give me any contact manifold in dimension at least 7, which is almost Weinstein fillable, and then also assume that one is torsion, then you find infinitely many Liouville fillable contact structures that are not Weinstein fillable in the same almost contact class. So again, Liouville but not Weinstein fillable structures exist in abundance in high dimensions. Okay, so if we revisit the hierarchy of fillings, but now for the case of the sphere, so we simplify the topology as much as possible, and then we look at this sort of set of inclusions, that on the sphere of dimension at least 5, we'll still have an equality of Stein and Weinstein, and then we have a strict inclusion for Weinstein G Liouville if we assume dimension is at least 7. And then we have the other inclusion. So the last inclusion is strict by our result, the first one that I mentioned. It's known, it follows by a result of Massot and Wendell that there's an equality at 2. So strongly fillable contact structures on spheres, I'd say things weakly fillable structures on spheres. Basically because the symplectic form is exact near the boundary. And then this deformation argument that you can use, which goes back to the Algebraic. And if n equals 1, so for the 3 sphere, the result of Algebraic that I mentioned before says that everything is an equality. Okay, so but then there's one sort of inclusion that remains that we don't really understand. So we don't know whether it's strict or not. So the open questions that remain is sometimes, well, first of all, for dimension 5, we don't know whether there's a Liouville but no Weinstein fillable structure on S5. But I think more interesting is the second question: is there a strong but not Liouville fillable structure on the sphere of dimension at least 5? Okay, so this would sort of up to one of the inclusions, more or less we understand the open, whether they're strict or not. Any questions about the statements before I go into the constructions? All right, so let me sort of give you a construction of a tight and non-fillable structure on a sphere. So in order to do that, I need to remind you of a very sort of foundational correspondence between open book decompositions and contact structures, which is due to Zhou. So basically, Zhou dimension 3 proves very strong results, and there was also in high dimensions. So I will simplify the results to the following statement. So contact structures are supported by open book decomposition. So an open book is so away from a codimension 2 subset B of the manifold, then your manifold fibers are the circles. And the fibers are called pages of the open book, and they all have the same boundary at B. And then this notion of an open book supporting a contact structure intuitively basically means that away from a neighborhood of the binding, like in the picture, away from that, then the contact structure is more or less tangent to the pages of the open book. And as you go into the color neighborhood of B, then sort of the contact structure twists around and becomes sort of horizontal at B. So this is the picture that I'm drawing here. B is called the binding of the open book. And so what Zhou says is that if you give me any contact structure, then I can find one of these sort of open book decompositions, which is compatible with the contact structure in that intuitive sense. Okay, so this is a pretty sort of non-trivial result. So this is the input for a construction due to Bourgeois that goes back to 2002. So what Bourgeois does is, if starting from an open book supporting some contact structure, then he constructs a contact structure on the product of the manifold with T2. So the motivation at the time was some sort of like construction existence result. There was an open question ever since Lutz wrote down a contact structure on T5 in the 70s, and people didn't know back then whether high dimensional tori were contact. And this sort of solves that by iterating the Bourgeois construction. So the really non-trivial input of this theorem is Zhou's result. So this is a very simple formula one can write down and check this. Okay, this gives us some sort of systematic way of getting contact manifolds. Yeah.
So does the context structure on the right have a natural open book? Given
not as far as I know.
Oh,
It has a natural spinal open book, if you know what that means. And it inherits another type of fibration where the pages are the same as the original open book, but now the base is not the circle anymore, but it's T3. So there's a natural notion of fibration associated to the drama, but I don't want to get too much into that.
Is it just a product structure?
No, not really.
Okay.
I mean, yeah, not really. Okay, so let me give you sort of a geometric construction of one tight and non-fillable contact structure on the sphere. So the idea is the following. So you start with an open book on a sphere of dimension 2n-1, so 2 dimensions less than the one you will construct a contact structure on, and you take an open book on it, for example, one of these Milnor open books coming from hypersurface singularities. So for example, the AK singularity. And then you do the Bourgeois construction on that open book, so you get a contact structure on the sphere times T2. And then you basically simply kill the topology. So you kill the 2S1 factors on T2 by doing 2-1 surgeries. So you reach a sphere times S2. And then you will kill the pi 2. So now you kill the 2 sphere factor by doing 1-2 surgery. So now you reach a sphere. So this is a a smooth version. But if the dimension is high enough, so you're in dimension at least 7, these surgeries are subcritical. So you're only doing surgery up to sort of the critical dimension -1. So there's an H principle by Jaspers that gives you that you can realize this sequence of surgeries by a Weinstein coordinate. So in particular, you inherit a contact structure at the positive end. So you have one of these contact structures on a sphere. And the claim is that this is actually tight and non-fillable. Okay, so it's a more or less, so more or less geometric, except for the fact that, I'm using an H principle. So I don't really know much about what kind of structure I get. Only I know how we construct it. Okay. So I'm making two claims here, first tightness and then non-fillability. So let me focus first on how you would prove the statement on tightness. So in order to do that, I would like to sort of rephrase the notion of tightness and fillability from an algebraic point of view. So for that, we'll consider the contact homology algebra, which is a well-defined object by, for example, by work of Bowden. So the definition is, I will want to say that my contact manifold is algebraically tight if its contact homology is non-zero. And then we want to say that it's algebraically fillable if there is a DGA augmentation of the. And there's similar definitions for algebraically overtwisted and non-fillable. So namely, algebraic overtwisted just means that the contact homology is zero, and algebraic non-fillability means that there is no DGA augmentation at the chain level. There's some sort of algebraic notion, and I just want to make the following note. Despite the fact that at the chain level, the homotopy type of the contact homology algebra is not a well-defined thing, this definition is actually well posed because of the functorality properties of the DGA. Okay, so one can use sort of these properties of the DGA to show that this definition doesn't depend on underlying choices. Okay, so this will be the running definitions to prove tightness. So there's a bunch of formal properties of this notion, which are sort of coined in this lemma. So first of all, algebraic tightness implies geometric tightness, just simply tightness. So in other words, if you have an overtwisted contact structure, then the contact homology is zero. Moreover, algebraically fillable implies algebraically tight. So in other words, if you were not algebraically tight, this just means that so by the definition before, so algebraically tight means that the contact homology is non-zero. So if you sorry, what am I saying?
Like if it's zero, it can't have it.
Right, exactly. So if it were zero, then that is sort of precludes the existence of augmentations. I was just getting my definitions swapped. Okay, algebraically non-fillable implies non-fillable because fillings induce augmentations. And then there's a notion of index positivity, which was studied by Lazarov and Zhou, which is this notion of asymptotically dynamically convex, or ADC. And sort of this notion of one ADC. So this is a rather technical condition, but it's actually useful. But it just means that there should be a sequence of contact forms, which is sort of non-increasing, and then there should be a sequence of numbers going to infinity in such a way that all the Ray orbits whose action is less than those numbers, which are also contractible, then they have Collie-Zender index, which is greater than 1. I mean, it's a rather sort of technical index positivity assumption, but it will imply algebraic tightness. Okay, so I don't want to say too much about that, but so we will use this in order to show that our sphere is actually tight. So there's a bunch of facts too in this direction. So tight contact manifolds can actually be algebraically overtwisted, at least in dimension 3. So Russell Adbeck constructed an example of a 3 manifold for contact 3 manifold, which is actually tight but has vanishing contact homology, which is rather surprising, at least to me. So this really means that we should talk about these algebraic notions as being something worthy to study on their own. And then algebraic tightness is actually preserved under surgeries. So one would like to say that the same is true for tightness. So whenever you do surgery on a tight manifold, you still have a tight manifold. That is only known in dimension 3 by a result of 1. We don't know that in higher dimensions. But we do know that for algebraic tightness as it follows what functionality properties of the J. Okay, and then if you start and this will be sort of crucial for us. So if you start with the binding of a fillable open book, which satisfies this index positivity condition, then this stabilizes under the bourgeois construction. So this gives you a 180C algebraically fillable bourgeois manifold, which in particular implies algebraically tight. In particular tight, but most of all algebraically tight. And the way that I want to the reason why I want to emphasize that is because we did surgery on this, and then algebraic tightness is preserved under surgery, so we get the same thing at the positive end of this. So for example, if we took a Milnor AK singularity open book, then one can check that this was 180C binding. So if I start with the Milnor AK singularity open book on the sphere, I do the bourgeois, I still get one of these algebraically tight bourgeois manifolds. When I do surgery, I get algebraically tight sphere and particularly tight. So this is like, well, how you show tightness. So if you
algebraic fillability or non-fillability the same as is it strict?
Not as far as we know. Any more questions? So then the upshot of all this sort of formal discussion is that if I take a very specific type of open book on the sphere, satisfying that the binding has some positivity condition, then the end result will be tight. So, and one note that I want to make, so heuristically, there's probably many choices of open books to start with. So there's many examples of like open books with 180C binding. So this follows, for example, from work of Otto van Kurt or Quan van Kurt, so the study of Briescon spheres. So you can study many of those. So this suggests already by construction that there should be many non-standard structures on the sphere. But it turns out that distinguishing them is rather subtle. So I mean, it's not clear which invariant to use in order to say that if you start with different open books, then you do this, then you get different ones. But this is sort of like the heuristics. And if the dimension is high enough, then we can actually do that.
So is it known if these Milnor open books are Weinstein covariant too?
Like all of them between each other, you mean?
Yeah. Or do they just give the same context structure?
Well, they support the same contact structure, right?
Oh, okay. No. Yeah.
Okay, so that sort of proves tightness. How about non-fillability? So it turns out that this is more involved. So non-fillability of these exotics here can be proven by at least 2 different methods. So the first one is this idea of a homological obstruction and cobordisms. So this is similar to a construction that we did on a previous paper with Jonathan and Fabio, which building on ideas of Massot, De Kruger, and Wendell. So this is the sort of the approach that I will describe for you guys today. And then the second approach is using some symplectic homological computations that's done by Zhengyi. I will then sort of focus on the first approach. So what is this homological obstruction? So the idea is to prove that fillings of your manifold have sufficient homology. Okay, so the first observation is the following. So if I take a bourgeois manifold, by construction of the contact structure, it's actually T2 invariant. So there's an obvious action on T2 on the second factor, and the contact structure that you find is actually invariant for that action. So in particular, is S1 invariant in 2 different ways, so for each of the S1 factors. So I do the following, so if I do the following dumb thing, so I write my manifold m times T2 as m times 1 times S1, so I distinguish one of the S1 factors, then I can rewrite this in the following way. So as being obtained by gluing 2 pieces together, sort of V plus times S1 and V minus with opposite orientation times S1, along some gluing like phi, which is basically induced by the monodromy of the open book. And the key thing here is that this is a convex decomposition. So this gives us a manifold of the type manifold times S1, where the S1 direction is a contact vector field, so it preserves the contact structure. So this tells that the hypersurface m times point is convex in the sense of Zhou. So in particular, it comes with a dividing set. So it decomposes into a positive piece and a negative piece. The positive piece V plus is where the S1 direction is positively transverse to the contact structure. The V minus piece is where it's negatively transverse to it, and the dividing set is where it's tangent to the contact structure, which is the boundary of V plus and V minus. For the case of the bourgeois construction, this V plus and V minus are given by sigma times V star is 1, so the annulus, where sigma is the page of the original open. Okay, so I'm saying that I can view any bourgeois manifold as being of the form V times S1, where V is a convex hypersurface with some dividing set. So I will want to use a more general term, so by Jonathan, Fabio, and myself, for these types of manifolds, which includes in particular the case of bourgeois manifolds. So the theorem is that if you give me any manifold of the form V times S1, which is a convex decomposition, so it's S1 invariant, and I look at the dividing set, so the boundary of each of the positive and negative p's, and if I take any symplectic filling of this manifold, then I have the following claim. So I look at the inclusion of the dividing set inside each of the two pieces, V plus and V minus, and I look at the inclusion of V plus and V minus inside the filling, and then I look at the maps and do some homology. So I have a sequence of two maps. So the claim is that the second map is injective on the image of the first. Okay, so this might sound a bit mysterious, but so what this is saying is that if a homology class in the dividing set survives in each of the pieces of the decomposition, it also survives in the filling. So the filling needs to have sufficient homology in order to exist. Okay, so at least a homology of the dividing set inside the boundary.
Can you say a word about why we should expect it? Or why it makes
I'll give you an idea of the proof. So yeah, so this is what we call a homological obstruction, right? Because it obstructs homologically the existence of it. Okay, so let me sort of, as I said, give you an idea of the proof. So the way that you go about this is you start with your convexly composed manifolds, and then you can sort of do one of these capping cobordisms, which were studied by Zhou and Kruger and Mendel. So you can blow down each of the B plus and B minus sides. So you have a cobordism to the dividing set times the two sphere. So imagine like you take a color neighborhood of the dividing set, and then you glue in sort of V plus times disk. So sort of collapse the S1 factor, and there's two disks on one side and the other glued to a sphere. So this is the positive end of this cobordism, and this is actually a stable Hamiltonian manifold. So it comes with some stable Hamiltonian structure. And the way you do this is by handles which have co-cores, the V plus and V minus pieces. And so now the observation as the second factor of some dividing set times S2 gives you a moduli space of spheres. So they're holomorphic. Whenever you have, so if you have a filling, this gives you a moduli space of spheres in the filling, which is it comes with the mark point, so it comes with an evaluation map. You need to compactify and everything, and you might not have transality in general, so you need to deal with that. But anyway, so this is the structure that you get. And by construction, spheres intersect the co-cores of the handles precisely once, so you have an associated intersection map. So for each point in the moduli space, you associate its intersection with the co-cores. And then sort of you just conclude as follows. So you say if a cycle in the filling bounds a cycle coming from the dividing set, then what you do is you pull it back under the evaluation map to the moduli space, and then you push it forwards under the intersection maps to the co-cores. So, and this gives you a cycle that bounds sigma in the V plus and V minus. Okay, so if it dies in the filling, it dies already in V plus and V minus.
Sorry, can you explain again the last?
So I'm trying to prove that if something comes from the dividing set and it bounds something on the filling, then it already bounds at the boundary, so already in V plus and V minus. So assume that it bounds something, then I have a moduli space. I can pull back that cycle under the evaluation map. So now I have some cycle in the moduli space, and then I have this maps which push that cycle to the V plus and V minus just by intersecting with the co-core. And if you follow the diagrams, the boundary of that thing will be the boundary of your original cycle. So you do everything relative boundary.
Why is B a cycle of higher dimension than sigma?
A cycle.
So there's B, which is you take the inverse of sigma by evaluation, but push it to V plus
No,
minus.
it's a cycle of the same dimension as sigma.
But you're saying it.
Sorry, it's a cycle of one dimension more than sigma. Oh, sorry, there's a typo here. There should be C. There should be a C.
Oh,
Sorry.
Wait, or should it be?
Maybe
sigma?
sigma should be C. This should be a C.
Yeah, that makes sense.
So yeah, so if you replace sigma with C, so that's the thing that you want to be the boundary or something. Sorry. Okay, so this is like the idea of a proof. And the idea would be to try to leverage this for our situation. So first of all, there's the following fact. If I do my bourgeois manifold as one of these convexly composed manifolds, I will do surgery on that. And if the dimension is high enough, subcritical surgeries on this bourgeois manifold can actually be pushed away from the dividing set by dimensional reasons. So in particular, after I do surgery, the sphere that I get still has the dividing set n naturally included there. And if you follow, so because you did some critical surgery, the homology in degree n is not changed. So in particular, it's still non-zero at the positive end. So there's some homology, so there's some subset with non-trivial nth homology on the sphere. And then the claim is that, well, you can actually sort of generalize this homological obstruction theorem for surgeries away from the dividing set. So the picture is, there's some clever sort of sequence of covariables that you can do in order to get this. So you start with your sort of convexly composed manifold. So this is V minus times this one, V plus times this one, and then here's the dividing set times V star is one. So you will do some surgeries away from the dividing set. So you get this new manifold here, which has this boundary here with the surgeries, which are away from the dividing set. So this in our case would be a sphere. And then there's another covariism that you can do. So you want to sort of mimic the previous proof for now for the sphere, which still has a dividing set over here. And what you do is you blow down the other component of which you didn't do the surgery. So you attach a handle of the form V minus times this. And what can see that the resulting manifold, this red thing, this which I'm calling M prime, has an open book decomposition with no monodromy. And the page of the open book is just obtained by V plus by doing a sequence of surgeries corresponding to this handle attachment. So this is a V prime plus. Okay, and then now you have this manifold, and you can still do the previous proof as before. So there's another sequence of covariations that take you to V plus prime times S2, and then you run the previous proof. Okay, and the thing to observe is that the nth homology of V prime plus is the same thing as the nth homology of V plus. Okay, so then there's some sort of clever sort of sequence of surgeries that you can do and show that sort of this homological obstruction theorem stabilizes under surgeries. Okay, so, and that basically sort of all the ingredients that you need to finish the proof. So the end of the proof is you assume that you have a filling of the sphere up there. So if by construction it still has the dividing set sitting over it with non-trivial nth homology. So the homological obstruction theorem leveraged tells you that the filling should have non-trivial nth homology coming from the dividing set. But however, this factors by inclusion through the sphere at the boundary. So the sphere to n plus one dimensional sphere has no nth homology. So you get a contradiction. Okay, so that's sort of how you prove non-fillability. So you have sort of this homological obstruction thing for convex decomposed manifolds, in particular for the bourgeois, and there's a way of sort of stabilizing this under subcritical search. So that's basically the end of the proof. Any questions? Maybe that was a bit too fast. Okay, so that's one construction that you can do, and then in order to get more, then you have to do some more tricks. So let me just give you a conjecture. So the conjecture is that if I take this exotic sphere that we just constructed, I want to conjecture that the connected sum of this exotic sphere with an arbitrary tight contact manifolds should actually become non-fillable. So in other words, there should be fillability obstructions on non-standard spheres, like in the same sphere as Zhou torsion, but with completely trivial topology that you can implement anywhere else. So I mean, we know this for strongly fillable contact manifolds with C1 torsion. I would like to say that those are technical assumptions. And we sort of know what would need to be implemented, what kind of machinery would need to be implemented for this conjecture to be true. So first of all, this would need some formal, so like, let's say, making the work of bourgeois and Eliashberg on the surgery formula for DGAs rigorous. And then the second thing that this would need is that for any augmentation epsilon, there should be a notion of a linear symplectic homology for this with respect to this augmentation as an invariant of the contact structure and its associated structures. So there's two perspectives that you can take on this. First, you can define this using Hamiltonians. The technical difficulty most likely will be setting up arbitrary functoriality. Or you could sort of try to define this as some version of linearized non-equivariant contact homology, which will probably make arbitrary functoriality easier, but the result of Chirivak may not be directly used in the case of subcritical handle attachment, saying that this should be vanishing. Okay, so what I'm trying to say is like we have this sort of conjecture, which seems like there should be some sort of very general fillability of structures, and we know precisely like what we would actually need in order to set this up. Okay, so let me sort of give you sort of for the end of this construction. Let me just give you a bunch of remarks. So I just give you one geometric construction. How do we get like that it's homotopically standard so that the underlying formal topological data is not changed? So if you fix the contact structure of the original manifold, then if you do the bourgeois construction, then the almost contact structure is just that psi plus the tangent bundle of T2. So it only depends on psi and not on the open book. So it suffices to look at the case of a trivial open book. And that's sort of easier to track. So when you do the surgeries, then you can check that at the end of the day, you get a standard, almost contact class of the sphere. And well, you also have to use the H-coordinate theorem to say that you have the actual standard smooth topology of the sphere at the end of the day. For infinitely many, I mean, you can take connected sums with the examples of Lazarev of non-standard flexibly fillable spheres, and then those are all distinguished by a positive version of symplectic homology as introduced by Chile-Wancha. So you need to first check that it's well defined, and this is why we need this 180C condition. So you can check that if you have this index positivity condition, there's this well-defined positive symplectic homology for a contact manifold. Dimension 5, so everything that I did before was for dimension at least 7 because we needed sort of subcriticality. Dimension 5 needs a careful, flexible version of the homological structure. So for flexible as opposed to subcritical handle attachments. So dimension 5 is rather special. And then symplectic homology approach, which I didn't mention at all. Well, so I kind of mentioned the Kaplan covariations that go into this. So when you do this clever covariations, you reach the boundary of a stabilization, so of D times D2, so one of these stabilized manifolds. And Zhengyi has studied them quite systematically. So he has in particular computed the positive symplectic homology. There's also computations of quantum von Kurt for Briscoe spheres that can be used in this direction. Okay, so I will not get into that. I just wanted to mention that we can also prove non-fillability using these ideas. All right. Okay, so that sort of finishes like the construction of a tight but non-fillable structure on the sphere. Let me sort of like, I'm going to finish early today because it's early and this is a price talk. So let me just tell you how you would go around construction of Liouville but not Weinstein fillable structure on its sphere. So again, there's a one geometric construction, and then you have to work harder. One example of this is the following. So you take a Liouville domain, which is of the form manifold times interval. So this exists by work of Masoni, Recurrent, and Wendell in n dimension. So dimension 3 was already known before. This is also examples of dimension 5 by Geiges and so on. But anyways, you take one of those, and then what you do is you stabilize it. So you take its product with the 2, and you look at the boundary of that. So that's some contact manifold M, and you can check that it's sort of ADC. So this was checked by Zhengyi. And what you will do then after this, well, first of all, this M has a stably trivial sort of tangent bundle. So there's a result of Bowden, Crowley, and Lipschitz that give you a cobordism W to a sphere. And then you use Chilibak-Eliashwer's H principle to say that, well, this cobordism can be realized by a flexible Weinstein manifold. So in particular, you inherit the contact structure in the positive end. And you can also check that it's ADC. So in particular, Zhengyi's results and fillings for this apply. So now you have this stabilized manifold, and then you stack this cobordism on top of its natural filling, so V times V2. So you have a natural Liouville filling of the resultant sphere. But we want to say that it's actually not Weinstein fillable. So the first observation is that if n is at least 3, so we're in dimension at least 7, then X itself, so the natural filling that you get cannot be Weinstein just by topological reasons. So the 2n minus 1 dimensional homology is non-zero, which is coming from the fundamental class of this n of the sort of n in the product of B. So this is a slightly tricky thing. So dimension 7 is different from dimension 5 in this case, because for n equals 2, this manifold is actually Weinstein by result of Breen and Christian. So if you take a non-Weinstein Liouville domain in dimension 3 and you stabilize it, you actually get a Weinstein. So this is why we cannot get a result in dimension 5. And now you can sort of use the fact that you have this positivity at the boundary. If you have any other fillings X prime of the sphere, because you have ADC, then Zhengyi tells you that the homology of this arbitrary filling W prime coincides with the homology of W, but in particular, it cannot be Weinstein. So in other words, the sphere is not Weinstein filled because all fillings have the wrong homology. And that's it. So in some sense, well, I don't want to say it's simpler construction than the previous one, but we had to work less, just like you combine well-known results in the literature. So that finishes the talk. Thank you.
Very much questions?
Can you say again what this ADC condition means and why is it good? Like you said, it's useful.
Right. So it's not good in the sense that it's hard to state.
Yeah.
That's a sort of disadvantage of it. So the definition is, well, basically, there should be a sequence of contact forms which are non-increasing. So alpha 0 is less or equal than alpha 1. Well, that just means that one is a positive multiple of the other, right? And there should be a sequence of positive numbers going to infinity, which are going to be actions. And the property is that every orbit which is contractible and has action less than those numbers for the contact form alpha I, say, those have Conley-Zender index Conley-Zender index which is greater than 1. Okay, if it sort of just complicates your head, like just think of a case it's like just one contact form. You just want to say that, well, the Conley-Zender index should be greater than 1. I mean, it's just some sort of index positivity assumption.
It's like a weaker index positivity.
Yeah. And the reason why it's useful, first of all, is they exist. They tend to exist. It's a rather flexible enough.
Yeah, but then you can do some like filtration limits on
Right.
the symplectic homology, and then that's the point. And then
Yeah, and then it's sort of well behaved on the surface. This is something what we've been using.
And can you go back to I just wanted to look at the
And maybe another thing is that that definition already gives you well-definedness of positive symplectic cohomology.
Ah.
So what do you want to do?
No, I just wanted to look at the theorem by Zhou.
So the theorem of Zhengyi says that if you have an ADC contact manifold, then the homology of the filling the homology of the filling is independent on the fill.
Any other question? Okay, so early. So let's take our speaker.